Looks like you found that switch, Jim.
Yeah, I remember years ago when we went through that. And I remember you or somebody, I don't know, I read back. Yeah, yeah. It's a long time ago.
Yes. Watch the stream. All right.
Oh, good morning. How you doing?
I'm all right.
All right. Not too bad. Not too
Friday
bad.
is good, huh?
Yeah. Hey, you can't go wrong with Friday. Never a bad thing. Never.
Only Thursday.
Here. Morning.
Good morning.
Morning. Yep. Hey, you. Yeah. Yeah, two more coming. One more coming. I'll give him another minute. Yeah. Probably or something. Okay. Well, good morning, folks. We'll get started here. Remember, I'm just Dave Kenny. Call me Dave. You should have these student notes from yesterday when you're here for the VAD box. And it looks like everyone's about it. We're going to go to air system components. The tab called air system components. All right. That's how they do. All right, good. Go ahead. You got to do. Oh, you got one more. Good. Oh, yeah. And okay, great. 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 All right. Now we got the good speed. So all you guys got to get it. No problem. All right, like I said, let's get your student notes open to the tab called Air System Components. It's the one you have for the DAV box. That's the book. But go into the tab and you'll find Air System Components. You'll be working in the middle to the back end today. Yesterday you were doing DAV boxes. Were there any questions about the DAV boxes that you were thinking of later? Probably not. But I'm sitting at the bar watching TV or something. Oh yeah, we'll talk about the data. Anything at all. Okay, today we're going to be dealing with the DAV air handler, the source of all the air and static pressures that we talked about. To that end, let's kind of just briefly go over what we're going to be getting involved with. Definitely getting involved with doing pressure checks around the air handler. We will do an overview of controls network. Not a big one, but enough to give you a little bit of knowledge on it. The commissioning class will have a 4-hour session on just VAS, so if you want to get a lot of in-depth, that would be the commissioning class. But I like to do an overview just so, as a task person, you know how this information is getting passed around. Definitely getting through the VAV air handler. We may get into the multi-zone, I'm not sure, but the focus is going to be on the VAV air handler itself. Okay? Going through all the components, all the 3 heats, cooling coils, dampers. Again, describing each one. You will also be using schematic. So we're going to get you to reading the schematic, labeling it, going out, identifying from the drawing to the components, make sure you're comfortable with reading a drawing set. Yeah, go through some procedures, sequence of operations. We're going to go through that as well. So those are the kind of things we're going to be talking about. I think when they flip the page over, then you should have this. Bring it page, you turn it over. It's on the back of the other first page, yeah. Don't know if Schneider went through this, but I'll go through it again to make sure. All the information about disconnects, labeling them, my panel name, where the power is coming from. I want to say the coordinates line of sight, but I'll stand corrected, but I'm pretty sure that line of sight for all of that. Really what they're saying is if you got a couple of pumps and each one's got a disconnect, you're having a problem with one of the pumps. Which one of these power sources, which disconnect are you dealing with? So imagine yourself being the maintenance people, and they got to deal with this pump. It's pump number 6. Okay, so where's the disconnect? Where's the power point? That's really what this is all about. If something were to go wrong, and you get to the disconnect quickly. That's really the essence. So you want to make sure you do that. Proper motor location, yeah. You got a centrifugal, got a wheel spin, right? Just because it's labeled doesn't mean the motor's going that direction. So in other words, when an electrician came in and reverses one of the phases, what happens? It goes backwards. If the motor goes backwards, will you get no flow, all the flow, or some flow of air? Yeah, you get some. Now the problem there is, I talked about yesterday, remember systems are designed for design days. So if you're in the spring and fall, you can get away with it. You just don't, you don't check it. But what happens on a design day, you don't think it's your fault. So you're looking at something like that. It ends up costing a lot of money actually in terms of energy. So you want to make sure you just book it, make sure it's going in the right direction. Coils, you'll be getting across the middle, which is part of your whole package. Giving you all the details on the coil, fins per square inch, design velocity of your line. I think Jim did cover a little of that yesterday. You want to make sure your piping is correctly connected properly. Parallel versus counterflow. What did you learn about that?
Cooling.
Counterflow.
The cooling coil.
Yeah, say the cooling coil. Parallel or counterflow?
Counterflow.
How come? You're right. You're right. Why would that
It's
be?
more efficient. More efficient.
Sure. It's kind of throw this out. So I got a cooling coil side view. I got airflow going this way. Okay. Chill water coming in, going this direction. Okay. So what's happening here is, oops, yeah, I got it the wrong way. Here. So you got a coil, you got 45-degree water coming in. Of course, you're going to have some passes, and if you're at full load, you might get a 55-degree water out. 10-degree delta, right? So what's happening here is the surface of this coil is approximately, given an approach, approximately 45 degrees, right? And then this surface is approximately going to be 55 degrees. What's going to happen is, and we'll assume too, we're in Florida, so we got not only dry bulb, but we got wet bulb, humidity, right? Dehumidified. We'll assume we've got that. We'll assume we're in the summer, got a heavy lake load, a lot of humidity, and you're sensible. So the air hits this right here. What begins to happen is you begin to sensibly cool. You're starting to drop the dry bulb temperature down. Okay, and as it begins to penetrate more and more and more, you begin to hit this surface. As you get closer to this surface, you're going to be at dew point. Well, hopefully you're going to be at dew point. What happens when you're at dew point?
Water
Condensing. You're going to condense. So there's your drip pan, and now you've got your condensate coming down. So you lower the sensible, and you also did the dehumidification. So this is like your pre-cooling, and as you walk through it, you begin to approach the saturation line, which again is dew point, 100% humidity. Contrary to belief, the air right here is 95% RH. That can't be. No, it's all dry. No. But you've lowered the amount of water in the air. Okay? The grains, per pound of water is going to be less. So you've dropped the dew point down. You bring down the water. But in order to condensate, you have to be at 95% RH, or you won't get any condensation, right? So that's kind of counterintuitive, but that's the way it works. So you want counterflow because you got your air going this way, you got your water going this way, and you're absolutely right. It's more efficient. What happens if you did it backwards? Let's go this direction. So we're coming in here at 45, and we're leaving at 55. So right now, we know the surface right here, the face of this coil, is approximately 45 degrees. When the air hits that, you're not only going to do a lot of sensible, but you're also going to start to deepen the climate. Well, what's wrong with that? Well, you're wringing out moisture, but you have high velocity air, which can pull in trains and pull that water right back into the coil. Some of it. So not all the condensate is going to go into the drip fan. You're actually pushing it right back into the coil. You're putting those BTUs right back into the air. Okay. So this is what you don't want to do, because now you've got parallel flow, air and water going in the same direction. And that's how it works. So that's why you always want to do counterflow. If you had a situation like this, yeah, it would work, but what could happen is you start getting people uncomfortable in the room, almost like a hot ball. They're saying, wow, I'm cool, but I'm planning. That kind of a situation. And people are going to start saying, wow, what's the matter here? And they're not going to run to this toilet check because it's already fully occupied, everyone's gone. And what's going to happen is they're saying, well, how can we fix this? Well, I know what we'll do. Hey, we'll fix the problem. We'll call the central plant, and we'll have them go into your water. We'll drop it down. The chiller was designed at 45 degree discharge. Get the most efficiency. We're going to drop the chill water down to 43 degrees. Well, in some ways you'll make it worse, but more so, what did you just do? What happens when you drop that water down to 43? Think about the big picture now. Think about the central plant. Sorry? Yeah, the compressor's going to work harder, right? And that means you went below design. Design was 45, you went down to 43. The chiller can do it, but it's going to start doing a lot more work. kW per ton. Okay, for every ton of refrigeration, what kW, how much power did it take to accomplish that? And that's directly proportional to money. So you're right. You put that thing over 10 years, you lost a lot of money. And if you have 20 air handlers, all type the same way, you can imagine how much work that should be. So that's why a simple little thing like checking and making sure you got counter flow is the way to go. Make sense, all that? So we did all that, checked it, pressure taps, air vents, make sure you got airbound, right? If the coil is airbound, is that going to damage the coil? Or what's wrong with that? You got air inside that with some water.
Be less efficient, and you have much less heat transfer.
Got it. You're limiting the surface area to do work, and you're going to have a lot less efficiency. Coil drain, we're talking about the blowdown valve. So maybe you got a big air separator at the bottom of it. It's going to be a hose, a guard hose with a little hand valve. That's just so that people want to clean out all the slag. They just open up that valve and bring it out. But you're going to get that in water anyway. What they're recommending is a gate or even better yet a ball valve. The simple reason is you can clean it. Because your ball valve is a line of sight valve, right? When you open it up, you can look right through it. Little details, but thinking about the overall picture of the maintenance folks, it's a lot to consider. Blow valves are great for me for controls. Yeah, they're great for metering water. They're more expensive, but you cannot look through them with a machine. It's not going to happen. So you cannot get in there, which is good job through it. It's not how it's designed. So the big thing to do there again is your ball being out. Pretty much on hot water, we see.
I'd like to add a little personal thing to that,
Sure.
the coil drain, and that's for you in this room. There's a lot of bacteria in this, so and they end up clogging up the drain line. So if somebody comes and says, "Oh, my coil's not draining, I need help," basically tell them to clean it out. It's nothing on your part to do at all as a design engineer. Administrative, absolutely nothing to do that. Only clean it out, and they should wear gloves, and they should wear a mask.
Good point. Very good point. Because you never know. You can know who knows what's going on.
Yeah, exactly.
You want to like being around cooling towers. You gotta be careful.
Yes.
You can know that it's for real.
Yeah. We used to,
Yeah.
we had these huge fan rooms on a submarine, and they would get clogged up periodically. And when we weren't paying attention, and they get clogged very fast because all the air is recirculated. So there's guys that are constantly sick, and most of the guys are never sick, right? But that's all bacteria in there, and it turns into a big, I call it a condensate book. If you go in there later on after it's all clogged, stick a little air hose, 20-pound air hose at the bottom of it. When you turn that on, the pressure starts to build up underneath that. But eventually, it pretty much explodes into the fan roof. And then there's bacteria and stuff everywhere. You can clean that up too. So that's
Good
about
point.
3 hours.
Good point. Thank you. That's a good point. Yeah, it's to be taken serious. Anything on that page? I think the next. Just copying the next tab. Did Snyder talk about this yesterday? I'm not sure. Sometimes we overlap, and I don't want to overlap. So. Okay. Here we're talking about the drain, condensate drain, and you have two issues of where this thing will be placed. And we have some on that multi-tone, but also one over here you can take a look at a little bit later when we get into the last portion. As to when they're making this thing, the heights have a lot to do with, is this a draw through, in other words, on the suction side of the fan, or the discharge side of the fan. That's really what they're talking about. And they're giving you the different measurements based upon the static pressure that's in that chamber. Okay. So if you have a draw through, which means you're on the suction side, this should be left open. The height from here to here is going to be based upon your static pressure. Okay. So they're just giving you, like over here, this height minimum. They're saying inlet pressure is 1 inch water column, and then they're going to have this to be that half that amount at least. Okay. So these are the things you can check when you get out there, and you'll see them when we get out to the lab itself. Another thing to consider should be this. This is a freestyle. Whatever you want to call it. This will be in the mixing chamber. And this will be in the mixing chamber of the air handler. The basic mantra is after preheat, before cooling. You leave it. After preheat, before cooling. The idea is you're trying to protect the cooling oil from freezing, which is a whole big game. What happens here is this is a straight-on view looking at it. There's your electrician's box, and then this isn't actually capillary. This is not made of nickel like some sensors. This is a capillary in that capillary buffer. So what, and of course, as we've shown it, it's what's called an averaging configuration, which always inflates the airplane. You want to have that not being averaging. How come? Why is it always averaging? So you got your outside air dampers, and then you might have a preheat coil, and right after that, you're going to have the averaging sensor. Why is it happening? Let me just put a little fluid right there when we're done with it. You're in here, Sorry?
Yeah, the cold air runs across the bottom.
Sure. Remember that the colder the air is, the more dense it is, the more it's going on the bottom. So you want to cover that whole area. That's why it's always going to be average. So the idea is, if you get below a certain temperature, it's going to shut the whole system down. That's what they're saying. So we're going to try to protect it. So what would happen is the dampers would close, the fan would go off, and all that kind of stuff. And that's what would be going on. So what happens is you've got this capillary. Right here is a set of contacts. The electrician then will wire those in series with the starter, which is right over here. Okay. That's the whole idea. So what will happen is, as colder this gets, you're getting a change in temperature. What happens to the refrigerant is making a change in temperature. It changes phase. Yeah, it changes phase, which is what it's supposed to do. And that in turn will change the pressure, which will then open up certain contacts. You get it normally open and normally closed. Typically, they use normally closed contacts in series with the starter right here. So here we got your lower line. These could be pressure switches. These are extra safeties that are in there. So this whole thing, along this leg, all safeties. Smoke detectors on the on the supply side, smoke detectors on the return side. Always normally close contact. Here's your HOA. And right now, it's set up to be in the auto position. Along in series with that is the relay from the controls. This is the actual, all it is a set contact. It's a relay, right? Single coil contact. You've got that coil right here, such that you want to start the fan, you energize that relay, close to the contact. You have continuity all around. In this case, it's sending out 120 to the contactor. They're pulling for 6 hours, then you're good to go. Now, all of a sudden, you get down to 40 degrees or something in the mixed air plenum. This opens up. What happens? Everything shuts down. And you build all the power to start it. So your fan will knock out your dampers and all that will go to their normal closed position. We'll talk about it more in a little bit. And it's as simple as that. But it has to be checked. Because a lot of guys that I used to know traveling, did a lot of traveling, checked out jobs. And they found out that the presets were there, almost 50% didn't work. Wow, that's scary to think about, especially in a northern climate. That's scary to think about. This is supposed to save you. And what would typically happen is, you install guys into this vent right here. By doing so, they're blocking the refrigerator. And that's what happened. They wouldn't work. Or it wasn't wired properly. So it was started. So there's two things you got to do. Car down the air handler, you get your all your gear on, safety gear, and you can do a couple of things. Get a pair of get a meter across the continuity, contacts, fans off, everyone can get stuff locked out. You can get a bucket of ice, or you can use the keyboard stuff, which is really cool. And you can make sure that first of all, there's a contact open. That's the first thing. The other thing to do is then power up the unit. Okay, you come out now, take off your meter, power up on these little, right on this little box, there's a little override switch that you kill when you open up those contacts manually. Then you can push that. Now you're verifying that the electrician did their job. Remember, there's 2 people involved here. You've got the install people over this side, you've got the electrician on this side. There's two stages you got to go with. And you verify you're good to go. But absolutely, yeah, this is not even an option as far as I know the cooler is pretty active about it. So, yeah, thank you, manually stuck. Exactly right. Taking the static pressure.
You put something that makes it verify.
Yes, sir.
Start.
Put down the coffee, go out to the, what happened. Because anything could happen. Maybe the damper outside here, we didn't close all the way. We don't know what happened. All we know is this thing is there. So you think about safeties, they are there to insurance policy. You want insurance policy. And these are, if they're installed right, they'll run almost forever. That's the way it goes. I remember writing code, having a salesman saying, hey, we want to save some money, we want to take this out. You write a software routine to do this and that. Yeah, but I'm not. Not doing it. Well, why not? Because it's a piece of software. That Tupperware there versus this thing, my money's on this thing. This is a hardware interlock. I'm here to go. I said, unless you get it right, you want this bigger. In the end, it's the right thing to do, right? The pressure switches, this is what I like high static. High static cut out for a heated air we're getting into. You absolutely, at that fan, you can run away. That duct was only rated for 3 inches. This thing can deliver 6 inches. You're in serious trouble if you don't have a high static cut out. So all these safeties are very important. Of course, smoke is what it is. When you get the smoke detectors in this situation, the fire marshal would say, we want you to shut down the system. This gets a lot dicier. Getting smoke control is way beyond my scope, and you can spend a whole day or two just on smoke control. So you could be doing 25th floor above, floor below, you're trying to pressurize stairwell. Ooh, that's getting a whole different ballgame. But what I'm getting at here is you're saying, well, how can you get involved with your air handling? On fire systems, which we're not, the primary people are responsible for get out of the building, move, that's number one. We can't get involved in that, I never did that. But as a secondary system, whatever the fire marshal wants to do, let you get away with it. And you might be going, yeah, what I want you to do is in this case, just shut down the system. Okay? So there's a lot more to it into this. All these contacts should be monitored by the head. We'll talk about it a little bit more. You can see all of them. Anything on safeties, real important stuff. Yeah, if you don't see them, you don't sign off. No, you don't sign off on it. All right, going to change directions just for a little bit and then get into some overview of controls networks. So let's do that, and then we'll get back into the air camera. While you're looking at this, let me put a drawing up here. Basically, you can break down control networks into two tiers, a higher level and a lower level. Okay. Let's talk about the high level first. So what that would consist of is all these are Ethernet devices. Everything is standard IT. Okay. Every controls contractor has to abide by it because we have to be web enabled, which I'm not going to go into because you can't do that, but it has to be there. But as far as the local area network is concerned, it's a standard Ethernet right out of the shelf, stuff you have in your home. It's no different if you really think about it. I can have on the local area network a laptop. Actually, I've got 3 of them connected. In this lab, I've got 3 laptops, and OWS is operating workstation. That's where you sit. There is absolutely no logic in here. This is a window. This is just a window. You don't have end gates here. You don't have windows looking into other devices. They're doing the work. They're controlling the building. So you've got this situation where there's peer-to-peer. Well, they're just computers talking. No big deal. Just chatting away. It's over an Ethernet kind of a thing. So what would happen is if you're sitting here, oh, by the way, you can have as many of these as your budget allows. Well, I mean, that does have some finite, but basically it's not a big limit at all. Okay? So you've got these guys. These would be vendor dependent. So GCI or Andover or Siemens, they're all good people. They'd have these things called supervisory controllers. So this is the window into the system. These things here are actually high level. They're supervising the lower tier. There is logic in here. Okay? There's features like, a weekly schedule, a demand limiting, whatever the features they want to have, trend logs and stuff like that. They're built in, and they're here. What they do is they oversee the lower level. So what that means is the second tier goes like this. This is a field bus. Typically, it's an RS-45, three conductor, positive, negative reference, whatever. And down here are your field controllers. Okay. So that little guy right there, that thing right there is a field controller. There's a field bus. Right now it's disconnected, but that would be the field bus. It's daisy chain. You cannot do a star configuration. It's daisy chained in. So 3 wires into one connector, one controller, 3 wires out the next controller, and so on and so on. So you've got these. This is where the action is. So when you have a digital controller, it's programmed by the vendor to do a function. This could be an air handling unit. This could be a central plant. You could have VAD boxes, and so on and so on. So they're programmed, they're standalone. So even if you lose a field bus, you're not losing your building. You'll still continue to control your air handlers, your pumps, your boilers, whatever it is that's going on. Okay. So that download program is proprietary. Okay. You can also have another field bus, in fact, a lot more. You got another DVC controller here. We can have a York chiller panel. Or an ABB drive. Okay, we'll talk about that in just a moment regarding protocols. So you've got all these devices. So this is your lower level right here. This is your higher level on this side. The way I really think about it is, yes, there's some high level features. These are also data collectors. Okay. But remember, the whole object of the game is I want to window of my system in real time, right? That's what you want to do. The idea is you're sitting here and saying, okay, maybe this is page 2. And this thing is controlling air handling unit 2. You're saying, I want the discharge air of air handling unit 2. You request it. This thing says, oh, I'll go get it. Comes down, picks up the data, sends it back to you. That's simple. You're just moving data around. I want to override the cooling valve of this air handler. You request it from here. This comes over here and says, oh, I know where it is. Goes down and gets it. Tell this device to do it. Comes back and says, yeah, I did it. So these are really, yeah, there's features in here for sure, but they really are high level in terms of data collection. That's their whole job in life. Now, another thing that this thing does is long-term storage. In other words, let's say you're trending, collecting information about certain points in the system. These things are actually collecting the information, sending it back to this controller. These controllers do not have hard drives. Okay? They can only fill their buffer up so much and then they write over themselves. Or what happens is you tell these things that when your buffer is 90% full or it's midnight, upload everything to this thing. Of course, this is not a hard drive. So now you've got a hard drive collecting all this information and it's there for long term. So what you can do is after X amount of months, come in with an external drive, $100, plug it in, back it up, clear out that cache, and you're ready to start over again. You can collect this information for years and years, which in some places that's what they want. You get to ASU campus, they got all this research stuff. They want to know the humidity, they want to know the temperature 24/7. So they're the trends all the time. They're collecting that data in case of some kind of breach. They can go back in time and say, well, April 6th of 2008 at 8 o'clock, what was the temperature humidity in such a lab? You see how that will appeal to those folks. And that's all, no problem, this network like this. So that's really what you've got going. You're collecting data in real time and getting information. And it's always improving more and more. Let's walk around here. Bring your safety glasses. You don't need your books, but let's do a little walkabout and take a look at some of these devices. So if you've got your glasses, we'll come around this way. Regarding security, when you log in, say you're right here and you're logging into the system, or you're at your laptop, like I am here, tied into that head end back there, it's going to be a username password, right? That's what you should do. What you're doing is you set a browser to this device right here. Right? That's how you do it, and you look into it. So there's going to be that kind of communication handshaking going on. When you'll get a pop-up window that says username and password. Yes, they're there to help keep people out, but your password is there not. It's really there to say what rights do you have on that system. Okay, let me give you an example. So So I show up and I've got my first year out and I don't know squat about HVAC. But they hire me on. They're saying, Dave's a nice guy. He always gets the coffee, but when he logs in, he can look only. In fact, he can only look at air handlers. So I log in and all I can see is air handler. I can't see the chiller stuff. I can't see the boiler stuff. All you see is the air handler. So this gentleman shows up, 20 years of training. Oh yeah. When he logs in, he can see nothing but refrigeration. But he can do overrides. Okay, because I trust him because I know what he's doing. I know what he's all about. So he can go ahead and look at refrigeration stuff, override refrigeration stuff. You can't touch the air handlers, but he can definitely hang around with the chiller stuff. It makes sense, so that's his background. And as he grows into it, fine, we'll go into it. Neither one of us can make changes to the database. I cannot delete points in the software, any kind of objects cannot be deleted or added. I can't add a feature because that's not what I do. That's not what I should be doing. However, this young lady shows up. She's a building chief. Well, guess what? She's got administrator rights. She can do all the above. So you see how you can set up your passwords for particular people's skills. As soon as you log in, yes, you've been logged in, and there's a report that generates that when you log in, what did you do during that time? Should you override something? There's a record of you doing that, and that's good too. But if you're going to do an override, remember, release the override. Many times they don't. When you do an override, if you walk away, that's the same thing to lockout, tagout. You took the point away from the whole system. It's a done deal. So you want to make sure there's a record that you do that and don't release it. So you get the idea on the passwords. Regarding firewalls, we do not provide firewalls. No controls contractor provides firewalls. No. If we had to sell you a firewall, that means I got to hire 3 or 4 IT people 24/7 to do all the sniffing. We couldn't afford to sell you that. And neither could Honeywell, neither could any company. So that resides with the IT people, which it should be. It's their network. We're only visitors on their network, the way I look at it. So they're the ones that are going to take care of all the security. So your folks back, your different bases will be handling all that. So in regard to that, you have to keep clear about what you're doing. It makes sense. I don't want the liability of getting hacked, especially military bases. All of a sudden, it comes back to another more serious trouble. So we just say, we do have passwords. There is some stuff that takes place regarding the type of code we use, but we're not there beyond that. So any questions on that? The last thing is something called backnet and bond. I don't know if you talked about that at all this week. Any discussions at all this week about that?
Okay, that's basically what you guys were talking about.
Sure. Ethernet's always had peer-to-peer. That's not an issue. The issue was peer-to-peer down here. And that didn't exist until a couple of years ago. Because what